starts, welcome to Mootechie, your go-to place where engineering meets simplicity and clarity. In today's session, we're exploring the heat conduction equation in Cartesian coordinates, a foundational topic in heat and mass transfer. Let's begin our journey, moving slide by slide, breaking down every detail. Moving to next slide. Heat transfer processes. Heat transfer can be classified as a steady or unsteady state, also called transient process, depending on whether the temperature of heat transfer medium and food product changes with respect to time and/or location. In food and dairy processing operations, heat transfer often occurs in the unsteady state. However, the system cannot remain under unsteady state conditions indefinitely. Eventually, the system would attain a steady state once the temperature of the food product turns equivalent to that of the heating medium. Once the steady state conditions are attained, any additional amount of heat energy being transferred into the system is utilized for phase change rather than to cause an increase in temperature. Moving to next slide. Objective of conduction analysis. To determine the variation of temperature with respect to location and time throughout a body. Location of a point within a body, at which temperature is to be determined, is specified by choosing a suitable coordinate system amongst Cartesian coordinates, cylindrical coordinates, or spherical coordinates. Temperature at a point is expressed as T of x, y, z, t in rectangular or Cartesian coordinates for parallelepiped bodies, T of r, theta, z, t in cylindrical coordinates for cylindrical bodies, T of r, theta, phi, t in spherical coordinates for spherical bodies. For any irregular shaped body, generally rectangular or Cartesian coordinates are used for conduction analysis. Moving to next slide. General heat conduction equation in Cartesian coordinates. Consider a rectangular parallelepiped or control volume or element of sides delta x, delta y, delta z, parallel respectively to the three axes x, y, and z, as in a rectangular Cartesian coordinate system. Assume the control volume to be made from a homogeneous and isotropic material with the same thermal conductivity, denoted as K. Density of the element is ρ, and specific heat is C along all the directions. Consider unsteady state conduction, where temperature T varies with location and time T, with internal heat generation within the control volume. Moving to next slide. General heat conduction equation in Cartesian coordinates. An energy balance during a small time interval T can be expressed as energy in plus energy generated equals energy out plus change in internal energy. Rate of heat conduction in plus rate of heat generation within equals rate of heat conduction out plus rate of change in internal energy. Or Q in plus Q generation equals Q out plus delta E rearranging, Q in minus Q out plus Q generation equals delta E. Or I plus 2 plus 3 equals delta E. Moving to next slide. Net heat accumulated due to conduction of heat along all directions. Q in equals Qx in plus Qy in plus Qz in Q out equals Qx out plus Qy out plus Qz out. Therefore, net Q equals Q in minus Q out equals Qx in minus Qx out plus Qy in minus Qy out plus Qz in minus Q. The conduction of heat through the different faces of the control volume, Fourier's law is used. Let Qx be the rate of heat conducted in through the face AEHD along the x-axis. Qx in equals minus k times ay times az times partial t by partial x. Heat conducted out through the face BFGC can be written as Qx out equals minus k times ay times az times partial t by partial x plus partial squared t by partial x squared times delta x. Moving to next slide. Net rate of inflow of heat in the x direction. Qx in minus Qx out equals k times ay times az times partial squared t by partial x squared times delta x. Let the control volume dV equal delta x times delta y times delta z. Therefore, Qx net equals k times partial squared t by partial x squared times dV. Moving to next slide. Similarly, the net rate of inflow of heat in the y and z directions. Qy net equals k times partial squared t by partial y squared times dV. Qz net equals k times partial squared t by partial z squared times dV. The net rate of conduction of heat into the control volume is Q conduction equals k times the sum of partial squared t by partial x squared t by partial y squared, and partial squared t by partial z squared, all multiplied by dV. Moving to next slide. Total heat generated within the element Q generation equals Q dot times delta x times delta y times delta z, which is Q dot times dV, where Q dot is the heat generated per unit volume per unit time. Moving to next slide, internal energy of the control volume. Q internal equals m times c times delta t equals rho times c times dv times partial t by partial t. Combining the expressions, k times the sum of partial squared t by partial x squared, partial squared t by partial y squared, and partial squared t by partial z squared times dv plus q dot times dv equals rho times c times dv times partial t by partial t. Divide throughout by dv k times partial squared t by partial x squared plus partial squared t by partial y squared plus partial squared t by partial z squared plus q dot is rho times c times partial t by partial t. Moving to next slide. Special case, variable thermal conductivity. In case of non-homogeneous and anisotropic material, the equation becomes partial by partial x of kx times partial t by partial x plus partial by partial y of ky times partial t by partial y plus partial by partial z of kz times partial t by partial z plus q dot equals rho times c times partial t by partial t. One-dimensional heat conduction. Partial by partial x of k times partial t by pi partial x plus q dot equals rho times c times partial t by partial t. Moving to next slide, special case, constant thermal conductivity. For a homogeneous and isotropic material where kx equals ky equals kz equals k, then k times partial squared t by partial x squared plus partial squared t by partial y squared plus partial squared t by partial z squared plus q dot equals rho c times partial t by partial t. Divide both sides by k, partial squared t by partial x squared plus partial squared t by partial y squared plus partial squared t by partial z squared plus q dot over k equals c over k times partial t by partial t. Define alpha equals k over rho c. This is thermal diffusivity. Larger the value of alpha, faster the heat diffusion through the material. Using Laplacian, the equation becomes del squared t plus q dot over k equals 1 over alpha times partial t by partial t. Moving to next slide. Special case, Fourier's equation. When no internal source of heat generation is present, that is q dot equals 0, the equation becomes partial t by partial t equals alpha times del squared t. Moving to next slide. Special case, Poisson's equation. In steady state, where partial t by partial t equals 0, the equation reduces to del squared t plus q dot over k equals 0. Moving to next slide. Special case, Laplace's equation. In the absence of internal heat generation and steady-state conditions, the equation becomes del squared t equals 0. That concludes our session on the heat conduction equation in Cartesian coordinates. Thank you for staying with us through each slide and formula. If you found this session useful, don't forget to subscribe to Mootechie for more deep dive lessons in food and process engineering. See you in the next video.